Hello everyone, welcome to one more of our online lectures on HEMI 5030. Today's lecture is one of the last few that we will have before the semester ends. So we have 4 more lectures left, and so my plan for today is to look at a problem using Lagrange multipliers, one more problem using Lagrange multipliers on a holonomic system, okay, and then we will slowly look at the dynamics of a rolling coin, one of the seminal problems in dynamics. Okay, so the aim for today's lecture is we will look at a problem using Lagrange multipliers. Okay, and the second thing is we will start looking at the dynamics of a rolling coin. All right, so these are the two key things that we're going to be doing today. So problem using Lagrange multipliers, and then we will start looking at the dynamics of a rolling coin. When we do the dynamics of a rolling coin, you'll be introduced to the 313 Euler angle sequence. Okay, 313 Euler angle sequence is one of the many sequences that we can typically use in studying the dynamics of a rolling coin. Okay, but this is the most convenient and the most useful for us. All right, so we will start off by looking at a very simple problem using Lagrange multipliers first. Okay, so here is a problem. In this particular problem, what I have is the following. Okay, I have a semicircular fixed surface. I'm going to draw that surface here. So here is the semicircular fixed surface, and then on this particular surface there is a bead that is sitting at the top. So first of all, let me set up the problem by saying, okay, this is a fixed surface. Okay, and I guess approximately here is the center of that surface. I'm going to set up a coordinate frame starting there. Okay, so here is the y-axis. I'm sorry, sometimes I can't draw straight lines. So here is the y-axis, and here is the x-axis. Okay, so I'm just going to call this as ex, and then this is ey for me, and of course ez is coming out of the page, and let's call this as point O. Okay, now I'm going to have a small bead that is starting at this position right here. Okay, so let's say that this is the starting position for that particular bead. Okay, let's say that it has a certain color, and this bead obviously is going to start traveling, and then it's going to fall down and roll along this fixed surface. Let's say the radius of this surface is capital R. So starting from here, let's say that the radius of this surface is capital R. Okay, and we'll say that, okay, at some point in time the bead is at an arbitrary position, which I'm going to call by a certain angle. Okay, so here is the bead at some point in time. Okay, so let's say that starting from the point O, I'm going to draw a unit vector here, or I'm going to draw a direction here, which I'm going to call as ER. Okay, and then the direction that is tangential to the surface is going to be called as E theta. Okay, and of course ER and E theta are perpendicular to each other. Okay, so this is the particle P, which I'm going to call as that. All right, let us assume that the surface of this semi-cylindrical surface is rough. Okay, so this is a rough surface, which means that there is going to be some kinetic friction between the bead and the surface. So let us state the problem by the following words. Okay, a particle starts at the top of the fixed surface as shown. Okay, so this is the starting position. Let me label that. This is the starting position. Okay, so particle starts at the top of the fixed semicircular surface. Okay, and the coefficient of friction between the particle and the surface is mu k, coefficient of kinetic friction. Okay, so coefficient of kinetic friction between the particle and the surface is mu k, which means that there is a non-conservative force that is acting. Then what are the things that we need to do? Okay, this is the statement of the problem. Let's say that the bead or the particle has a mass m, so particle has a mass m, and let's say that we are sitting on the vertical plane, which means that acceleration due to gravity, acceleration due to gravity is going to be pointing vertically down. Okay, so this is the direction of acceleration due to gravity. Of course, you can also have this problem on a horizontal plane, but there is not much going on there. All right, so what are the things that we are supposed to do? Obtain the equation of motion for this particle. Okay, equation of motion for the particle. That's one thing. And then we also need to find out what the expression for the normal force of contact is. Okay, find out an expression for the normal force of contact when the particle is at some arbitrary position on the surface. Is at an arbitrary position on the surface. Okay, that's something that we need to find out. Then lastly, we need to find out the angle. Find the angle. Let me call this angle as theta, and let me mark that on the figure right here. So I'm going to call this angle as the angle theta. Okay, find the angle theta at which the particle separates from the fixed surface. Find the angle theta at which the particle separates from the surface. And this essentially means that because I have to find the normal force, I have to use the idea of Lagrange multipliers. Okay. Of course, this problem can also be solved using the Newtonian formulation. Sometimes it is easier to do it that way, but since we are doing Lagrangian mechanics, let us utilize the Lagrangian framework using the idea of multipliers to solve this particular problem. Okay. So I did some amount of cheating here by saying that, okay, to begin with itself, I have a frame ER and E theta that is attached to the particle. So let me call that as a frame F2. Okay, that is a frame F2, and then there is a frame F1, which is as seen by an inertial observer here. So what I need to do actually is to copy this figure. Let me take this figure. Okay. And let us start looking at this problem bit by bit. Okay, so I'm going to bring that problem here. So my solution strategy, of course, so solution, since we need to obtain the Lagrange multipliers. Okay, since we need to obtain normal force, normal force of contact, we need to utilize the Lagrange multipliers. Okay, that is the basic idea. Since we need normal force, we need the Lagrange multipliers. This is because the normal force is a force of constraint, and of course we will see that this is a holonomic system by inspection, and I will also solve a problem on a non-holonomic system towards the end of the semester. It's not something that I will skip doing. Okay, I will still do that. Okay, all right. And so I bring back our figure from before, and I'm going to clean this up a little bit. Okay, so we already know that this is a rough surface and so on, so maybe I can keep that, but let me get rid of that. I'm going to cut that off. I'm also going to cut this particle off from there. Okay, we know that it's a rough surface, so we don't need to keep talking about that all the time. I'm just going to cut that off. Okay, all right. And so here I have the following situation. So first of all, I have a fixed observer. Okay, here is the fixed observer, that is point O. Okay, that's a stationary observer, and there is a frame F1 that is attached to this stationary observer, so I'm just going to call that as frame F1. Okay, and then I have a frame that is attached to the particle sitting from the observer. I can see the particle using the polar coordinates in 2 dimensions, er and e theta, and theta is that variable. And here is further what I'm going to do. I'm going to call this distance from the point O all the way to where the particle is sitting. I'm going to call that as r of t. Okay, and I'm going to call that as a position at r of t, and for the time being I'm just going to let it be r of t. Okay, all right. The first thing is I need to look at the angular velocity of frame F2. Frame F2 has a triad er e theta. You got to be careful. Er cross e theta is in a negative ez direction, so the triad is going to be e theta er ez, or you can call this as er e theta and negative ez. Okay, that is also completely fine. And then we can say that the angular velocity of this triad with respect to F1, okay, so omega of F2 slash F1, and what is the direction of that? You'll see that that's going to be theta dot in the negative ez direction, so that's going to be minus theta dot in the ez direction. Okay, so that is the angular velocity of the triad with respect to an inertial frame. All right. Now what am I going to see in this problem? I see that there are how many configuration coordinates? This is in 2D, so we're looking at a planar problem, so I'm going to assume that this is a planar problem. Assume a planar problem. Okay, which means that the configuration coordinates there are going to be 2 of them, and you can either call them as x and y, or I'm going to call them as r and theta. Okay, so I'm going to call them as r of t and theta of t. Okay, there are 2 configuration coordinates. All right, what is the constraint? The constraint is that the particle has to be on the surface here, which means that at any given point in time r of t is equal to capital R. Okay, what are the constraints? Constraints are that the particle has to travel on the fixed surface of radius r, which means that r of t is equal to capital R is the constraint equation. So this is the constraint equation, so I just want to label that constraint equation. And the basic idea is, if I look at the number of degrees of freedom, okay, number of degrees of freedom is equal to the number of configuration coordinates minus the number of constraints and that's equal to 2 minus 1, so that's equal to 1. And if we were to find and of course the system is holonomic, this is fairly evident by looking at the constraint equation, so I'm not going to go ahead and prove that, okay. By inspection of the constraint equation, we can see that the system is holonomic. That is, the constraint is a geometric constraint. Okay, and so the system is holonomic, which means that we can actually come up with a generalized coordinate. So this implies that since system is holonomic, we can come up with a generalized coordinate. Okay, which I'm going to call as GC, where for a holonomic system, the number of generalized coordinates is equal to the number of degrees of freedom. And it's quite an evident choice for this particular problem that the generalized coordinate is going to be theta. Okay, it's fairly evident here. Okay, and it is evident by looking at the problem. That theta acts as a generalized coordinate. Okay, but the problem is this: if I make use of a generalized coordinate, I won't be able to come up with an expression for the constraint force, so I have to use the Lagrange multipliers and use the configuration coordinates. But if we use generalized coordinates, we cannot come up with an expression for the constraint force, which implies that we need to make use of configuration coordinates. And the concept of Lagrange multipliers to obtain the constraint force. Alright, so this is a key statement and something that we have reiterated in many of the problems that we have seen. Okay, so if we use the generalized coordinates, we cannot obtain an expression for the constraint force, which means that we need to make use of the configuration coordinates and the concept of Lagrange multipliers to obtain the constraint forces. Okay, all right, and so we come back to our problem, and it's a fairly straightforward one to see that our configuration coordinates are r and theta, and the constraint equation is r is equal to capital R, which is equal to the radius. So we start off with this particular information. So back to our problem. Okay, so back to our problem. Okay, so if I go back to our problem, the configuration coordinates r of t and theta of t. Let me write this a little carefully. Okay, I guess that doesn't look like an r and a theta. Okay, so my configuration coordinates are r of t and theta of t. And of course, if some of you have tips on writing much more nicely on the iPad Surface, I'll be very happy to listen to you. As you can see, my handwriting is okay, but it's not. I think it has a lot of room for improvement. So, if any of you is hearing this lecture, please get back to me with some feedback on how things are. Okay, and how one can improve their writing on the iPad Surface. Alright, so if I go back to my problem, I have the configuration coordinates and I have the constraint equation. I'm going to write it in the Pfaffian form. Okay, so the constraint equation is r of t is equal to r, which implies that dr by dt is equal to 0 because r is a constant. Okay, which implies that dr is equal to 0, and so the Pfaffian form is going to be 1 times dr plus 0 times d theta is equal to 0, and so for me the constraint number is j is equal to 1. Okay, so this is for j is equal to 1. This is the constraint number, and so if I do a comparison, okay, if I compare the above with the standard form of the Pfaffian, the standard form is it's going to be since there is only one constraint, right? Let me actually write the standard form. So this is I going from 1 to something, so this is a ji dqi ajt dt, and we are essentially saying that I is equal to 1 implies that q1 is equal to r, and I is equal to 2 implies that q2, which I'm calling as theta. Okay, which means that our equation, our constraint is 1 times dr, 0 times d theta is equal to 0. Standard form for j is equal to 1 is a1r dr, a1 theta d theta, a1t dt is equal to 0, which means that if I do the comparison, then these two are the same, these two are the same, and of course ajt is equal to 0, so which tells me that a1r is equal to 1 and a1 theta is equal to 0. Okay, and of course ajt is 0 as well, or a1t is equal to 0, and it can be proved that this is satisfies the test for integrability. Okay, can be proved this satisfies the test for integrability, and hence the constraint is a holonomic constraint. There are no other constraints for the system, so the system is holonomic. Okay, no other constraints for the system, which means since this is the only constraint, the system is holonomic. Okay, so since the constraint is holonomic, system is holonomic. All right, so this is the situation we have, and all we have to do is write the velocities, then start differentiating and be on our merry way to look at the problem on the rolling coin. All right, so far story so far is we have the constraint equation. We have the configuration coordinates as r and theta, as I've written here. You can call this as q1 if you want. Okay, this can be called as q1. You can call this as q2 if you want. Okay, and then you can compare this with a1 1 dq1, a1 2 dq2, a1 t dt, or a1 r dr, a1 theta d theta, a1 t dt. That's also the same thing. And by means of this comparison, the coefficients of the Pfaffian form of the constraint equations are obtained. It can be proved this is integrable, so the system is holonomic because this is the only constraint, and the constraint is holonomic. All right, so I'm going to move on. Okay, now we have to look at the velocity of the particle. Okay. All right, so to find the velocity of the particle, here is what I do. Okay, I come back to our figure here, and I say that, okay, I first write the position vector of the particle as r p slash o, and that's going to be r in the er direction. Okay, so I say that, okay, r of p slash o is equal to r of t er, which means that the velocity, and this implies essentially that rp is equal to r of t er, so that velocity is r dot er plus r e dot r. Once again, I'm urging you to resist the temptation to substitute r dot is equal to 0. Okay, that is a key statement that I want to make here. We can of course do it later, no harm done, but not yet. Okay, so which tells me that Vp is r dot er, and then r times this is going to be omega of frame 2 slash frame 1 cross with er, and so Vp is r dot er, and then r times minus theta dot ez crossed with er. You go back to our triad, it was e theta, er, and ez. Okay, which means that ez cross er is going to be minus e theta. Minus and minus becomes a plus, and this is typically the expression for a particle's velocity in the polar coordinates in 2 dimensions. R dot er, r theta dot e theta. Okay, so this is the velocity, which means that the kinetic energy can be easily written. Okay, so kinetic energy T is half m Vp square, which means that kinetic energy T is half m r dot square, half m r square, theta dot square. All right. So we got that going. What about the potential energy? I want to go back to our figure. I want to just copy that and bring that down here. Okay. So for potential energy, let me take some of these things from here. Okay. And copy that and bring that down here. So if I paste this situation, I see that if I call this as my datum, so I'm going to call this as my datum. Okay, this is a problem in 2D, so my potential energy depends upon the height of the particle from the fixed datum, either above or below. If it's above, it's positive; if it's below, it's negative. This is one of the most common mistakes that every person in dynamics makes, is if you don't account for the direction of the datum above or below the datum, then you end up in trouble. Okay, so if I look at that, here is the situation. So here is the particle. Okay, and I'm interested in this particular height. Okay, that's going to be my height h, and it's quite evident to see that h is r times cosine theta. So when I write the height, h is equal to r times cosine theta, okay, which means that my potential energy V in this case is mgh, and if you want you can call this as a height above the datum, which means that V, the potential energy, is mgr cos theta. Okay, once again I want you to say, okay, resist the temptation to substitute for capital R, little r here. Okay, so resist the temptation to substitute r is equal to r in V. Okay, this is a key statement. Okay, resist that temptation. Resist that temptation when you talk about the velocity as well. Resist that temptation. Okay, you can do that later on. All right, I write the Lagrangian. So L is equal to T minus V, fairly straightforward. So L is half m r dot square, half m r square theta dot square minus mgr cos theta. Okay, so this is the Lagrangian, and I also have a1r. I'm sorry, I just want to write this in the normal colors. Okay, so a1r was 1 and a1 theta is equal to 0, and that's one thing, that's the other thing, and typically we will have as many multipliers as you have constraint equations. Okay, so we will have as many multipliers as we have constraint equations. Which means that for our problem, we will have only one multiplier. And you obviously know that this is going to be the normal force. Okay, now don't forget that there is a friction here, kinetic friction, because we say that the surface of this fixed semi-cylindrical object is a fixed surface. Okay, so I first write the Lagrangian formulation using the multipliers. So the Lagrangian formulation using multipliers makes use of the configuration coordinates. Okay, making use of configuration coordinates, and we have two, right? We have two configuration coordinates, so let me underline this. So the Lagrangian formulation using the multipliers, here is what we have. Okay, so for I is equal to 1, we have q1 is equal to r, and so I have d by dt of dl by dr dot is equal to dl by dr plus qr nc, non-conservative forces if I have them, or torques if I have them, plus I have summation for j is equal to 1 to m lambda j ajr, right? Because this is for I is equal to 1, and then likewise I is equal to 2, where say q2 is theta, then we have d by dt dl by d theta dot, this is equal to dl by d theta, and then q theta nc plus summation j is equal to 1 to m lambda j aj theta. Okay, we start expanding and doing the substitutions and so on. So before that, we have to see what are our non-conservative forces. Non-conservative terms. We have kinetic friction. Sorry, sometimes this gets stuck when I write. We have kinetic friction. Okay, we don't have any torques, we don't have any velocity independent forces, so this is a velocity dependent non-conservative force. Okay, I just want to make a note of that. This is a velocity dependent non-conservative force, and we can essentially see that I want to take some shortcuts here so that we get to the problem on the rolling coin by the end of 1 hour's time. Now I want to take a shortcut and say, okay, if you look at the friction force, right, the direction of the friction force is going to be in the direction of negative E theta. Okay, so I'm taking a shortcut. I'm just skipping some steps. Okay, taking a shortcut, we can see that F mu k is going to be minus mu k times the normal force times E theta. Okay, that's something that you want to keep a note of. Okay, and then the position vector where this force acts is essentially going to be where the particle is sitting at that point in time. Okay, and then for the non-conservative force, the position vector from the fixed observer to the location of the non-conservative force. This is essentially Rp. Okay, and that's going to be R of T ER. Since I'm doing a velocity dependent force, I need R dot. Okay, so R dot of P from before is R dot ER R theta dot E theta, and so I see the following. Okay, Q R and C is going to be, for me, since I have only one, that's going to be F mu k dotted with dr dot P by dr dot, which is going to be minus mu k times n times E theta. Okay, I'm taking a shortcut. Okay, dotted with d by dr dot of r dot er r theta dot E theta. Okay, which tells me that QR and C is minus mu k times n times E theta dotted with ER, which is obviously 0. Okay, there is no doubt about this. Since the friction force in the theta direction, I'm going to see this affecting only the theta equation. And likewise, let's find out Q theta and C. Excuse me. This is going to be F mu k dotted with dr dot of where the force is acting to theta dot. This is minus mu k times n times E theta dotted with d by d theta dot of r dot er r theta dot E theta. Okay, which tells me that Q theta NC is minus mu k times n times E theta dotted with, you got to be careful, this is going to be r times E theta. Okay, which tells me that Q theta NC is actually minus mu k times n times r. So this implies that this is actually the non-conservative generalized force is actually a moment. Okay, so this implies that the non-conservative generalized force for the theta configuration coordinate is a moment, right? You can see that it has units of Newton meters. Okay, so the non-conservative generalized force for the theta configuration coordinate is actually a moment, which makes perfect sense to us. Okay, so this is what we have. This of course would have ended up being a force if at all, when I'm saying if, this would have ended up being a force if it were not zero, would have ended up being a force if at all. Okay, but here this is a moment. All right, now we come back to our formulation, we rewrite our formulation. Okay, so rewrite the formulation. We're almost there. Okay, so in this situation I have, for I is equal to 1, I have R is the same as Q1, so d by dt dl by dr dot is equal to dl by dr qr nc, and then since j is equal to 1, I'm just going to expand it and say that okay, this is lambda 1 and a1r. Okay, and then I is equal to 2, this is theta is equal to q2, and so this is d by dt dl by d theta dot is dl by d theta q theta nc lambda 1 a1 theta, where the Lagrangian was half m r dot square half m r square theta dot square minus mg r cos theta, and a1r was 1, a1 theta was 0. And let's start knocking off some of these guys off. Okay, so this term is going to vanish, so that's gone. A1 theta is also going to vanish. Okay, and so I start doing the partial differentiations and go on my merry way. So for I is equal to 1, I have, look at the Lagrangian, there is a term containing r dot. Do not do the substitution yet. So this is going to be d by dt of mr dot. This is equal to dl by dr. Look at that. There is minus mg cos theta. Then do I have any terms containing theta, r dot here? I don't have any other terms containing that. And so what is that going to give me? That's lambda 1 and a1r, right? So that's going to be the following. Okay, so that's plus 1 times 1 times lambda 1, so that's lambda 1 times 1, okay, times 1, and then likewise I keep continuing. Okay, here is what I end up having. For I is equal to 2, I'm going to have d by dt of dl by d theta dot, so that's going to be mr square theta dot. Okay, and that's going to be mg sine theta, and then q theta nc, that's going to be the following. Okay, that's minus mu k times n times r. Okay, and I'm also going to have this is 0 times lambda 1. Okay, so far so good. This is the situation that we are having in this particular problem. Okay, I made a mistake. There is something else that I need to add in here, so that's a quick fix. Okay, let me do that here. So this term here, before I go ahead and complete it, I see this is another rookie mistake I shouldn't have made. There is a term containing r here. Okay, there is a term containing r here, which means that this is going to be plus, okay, this is going to be m r theta dot square. Okay, and then I'm going to have plus lambda 1 times 1. Okay, that's going to be lambda 1 times 1. Okay, there was a mistake that I made here, so I just corrected that. Okay, this was the mistake here. Corrected a mistake. Apologies for that. Okay, And then I have one more thing where we say that the constraint equation is that r dot is equal to 0 or r is equal to capital R. And now I'm ready to do the substitutions actually. Okay, which means that if I look at the I is equal to 1 equation, I can see that this is d by dt of 0. That's going to be minus mg cos theta plus mr theta dot square, where I have substituted for r as capital R, plus lambda 1, which essentially tells me that lambda 1 is going to be mg cos theta minus mr theta dot square. Okay, and then if I do I is equal to 2, look at this, it's going to be d by dt of mr square theta dot, so that's going to be mr square theta double dot is equal to mg sine theta minus mu k times n times capital R. Okay, so I have two things here. This is the first one and this is the second one, and obviously you can see that the second one is going to be the equation of motion. So I'm going to cancel off some of these terms. I'm going to get rid of that. There's going to be a factor divided by m, and then I'm going to get rid of r square here. I'm sorry, I shouldn't be doing that. I'll be dividing by r here, and I think I'm missing a term here. I made another mistake. I guess this is a day for mistakes. This is mgr sine theta actually, I'm sorry. Okay, so this has to be mgr sine theta. Okay, and so this is going to be mg times r times sine theta as well. I'm just going to scoot this guy a little here and bring in my r here, so that's going to be capital R. Okay, and so if I do the connections, and I just want to point out there was a mistake that was made here. Okay, missed putting an R. Okay, and so my equation of motion, what should be the equation of motion? Equation of motion does not contain the constraint forces, so that's going to be the theta double dot thing. Okay, the equation of motion is the term not containing the constraint force, and that essentially is that guy. Okay, and so my equation of motion for this problem is the following: is theta double dot, that's equal to g by r sine theta, okay, minus mu k times n by the factor of r cancels off, so I'm going to be left with times an r by m. Okay, all right, and so this makes sense in this particular problem. This is the equation of motion, that's the key thing. And I'm going to take some other shortcuts here as well. There's lambda 1. I'm going to say I'll let you prove it to yourselves by doing the Newtonian mechanics and then showing that lambda 1 is actually the normal force. So note here, okay, note, I'm skipping a few steps. Okay, we can use Newtonian mechanics to show that lambda 1 is the normal force of contact between the bead and the surface. I will not be proving this. Okay, will not be proving this, and it's left as an exercise. Okay, just so that I don't make any more mistakes. Okay, all right, so what we find out from this particular problem in summary. Okay, so summary: equation of motion is theta double dot is g by r sine theta, minus mu k times n by r times m. Okay, that's the equation of motion, and the constraint force is the following. Okay, that's the normal force N is mg cos theta minus mr theta dot square. Okay, so this is what we glean from the problem. The problem is not done. We still have a little more to do. We need to find the angle at which it loses contact. So that's something that I want to do. Okay, let me write this theta carefully, properly. All right, this is theta dot square. Now we need to find the angle theta at which the bead loses contact with the surface. Okay, so here is what we got to do. Okay, so at loss of contact, my normal force is going to be set to 0, right? If that is the case, then I look at the equation of motion, which means look at equation of motion, I get theta double dot is equal to g by r times sine theta. I said the normal force is equal to 0 at the loss of contact. Now typically what I'm going to do is I'm going to say that, okay, I'll ignore the presence of this friction force for the time being. You know, this is something that we can also do, and what I'm going to do is I'm going to apply the chain rule. Okay, so this is just a trick. Okay, this is a trick to use for such problems. Okay, this problem. And what is the chain rule? The chain rule is that theta double dot can be written as theta dot d theta dot by d theta. Okay, this is of a similar form, similar to A is equal to V dV by ds. Okay, if I write that out. Okay, this you might have seen in undergraduate dynamics. So which means that you know, for me, theta dot d theta dot by d theta is equal to g by r sine theta, which means if I do the cross multiplication, I get theta dot d theta dot is equal to g by r sine theta, which means that if I assume that theta dot at theta is equal to 0, this is the starting position, is some theta naught, you know, and let's say it's negligible or something, is theta naught dot is approximately 0, some very, very small value, and I'm just giving it a very gentle shove, let's say. Okay, and so what I can do is the following. Okay, now if I look at theta dot d theta dot, I can say this is g by r times sine theta d theta. I'm sorry, I missed out on a term here. So this is sine theta d theta. I'm going to integrate this on both sides. I'm going to start off with theta dot naught and then go all the way to theta dot, and of course this is theta naught, which is 0, so I'm just going to call this as theta naught, and all the way to some theta. And in reality I should be using a dummy variable here. Okay, so to be more rigorous, we need to use the integration dummy. I'm not doing that. I'm not doing that in this problem. Okay, that's something that we got to use here. I mean, this is just semantics if you want to be a little more rigorous about these things. So basic idea is I have everything going on now. This is integral theta dot d theta dot which I can integrate, and I can obtain the following. So after integration, here is what I have: theta dot square by 2 minus theta dot naught square by 2, which we said was equal to 0. This is equal to minus g by r, because integral of sine theta is minus cosine theta, and so that's going to be cosine theta going from theta naught is equal to 0 to some arbitrary theta at some point in time. And so I can get rid of some of these things, so that is gone. And if I do the rest of the stuff, I'm going to be getting the following: theta dot square is 2g by r. I'm just shifting the terms, okay? So this is what I end up getting after the integration has been done. Okay, now I come back to our problem. So back to our problem. So let us say that at theta is equal to theta critical, the particle is losing contact. I'm sorry, something losing contact. Okay, which means that at theta is equal to theta critical, the normal force is equal to 0, which means that at theta is equal to theta critical, the normal force, which is mg cos theta, but this is going to be theta critical, minus mr theta dot square critical, should be 0. Okay, and at theta is equal to theta critical, theta dot square critical, you see, I'm just going to borrow what I have from here. So I'm going to take that creature and then plug that in there. Okay, so I'm going to say that this is equal to 2g by r times 1 minus cos theta critical, and I'm going to take that and plug it back in here. Okay, which means I get the following. Okay, n is equal to 0, right, which means 0 is equal to mg cos theta critical minus 2g by r times 1 minus cos theta critical. If I rearrange the terms, I get mg cos theta critical is equal to minus and minus here, so that's going to be minus 2g by r. I think I'm plus 2g by r, I'm sorry. Okay, that's 2g by r, and that's going to be 1 minus cos theta critical. For some reason I'm completely off kilter today. Okay, that's going to be, if I bring the terms, that's going to be 3g, and there is a factor of r as well, which I forgot to multiply here with, so that's going to be a factor of r here, and I should have that on the equation written. So that's going to be a factor of r here, which means that I can cancel off this guy with that, and a factor of m as well, which I forgot to write. So there's going to be m here. Okay, and that's also going to be an m here. Okay, m times 2g by r times whatever that thing there. So the factor of m is cancelled off on both these sides, which essentially tells me the following. Okay, so 3g cos theta c is equal to 2g, which means that the factor of g can also be cancelled off. So this essentially tells me that cos theta c is 2 by 3, or theta c is cos inverse of 2 by 3, and this is approximately, if I see the answer, this is 48.1 degree. Okay, so theta c is 48.1 degrees. So in summary, the equation of motion is theta double dot is equal to g by r sine theta minus mu k times n by m times capital R. The constraint force is N is equal to mg cos theta minus mr theta dot square, and then for the case of n is equal to 0, we get theta dot square at any point on the path is going to be 2g by r times 1 minus cos theta. And for the case of n is equal to 0, where I'm essentially this is by ignoring friction, and I can say that for the case of n is equal to 0, the angle at which contact is lost is at 48 degrees. Contact is lost when theta c is 48.1 degrees from the vertical position. All right, so that's the end of this particular problem. Fairly nice problem. I mean, it's a gentle problem. There is no doubt this is not that complicated, in my opinion. Okay, but I think it's a good problem that rehashes, what we do in the Lagrange multiplier method. We have a particle sitting on a fixed surface. We want to find out what the normal force of constraint is for the particle using configuration coordinates and Lagrange multipliers. Along the way, we find the equation of motion, and then we can also say that, okay, at some point it's going to lose contact, so the normal force is going to be set to 0, and at that particular location, what is the angle of theta? And that angle is going to be 48.1 degrees. All right, so that's the end of this particular problem. Now we move on to a slightly different chapter, a different flavor. Okay, we're going to move to the problem of a rolling coin. Okay, so we are now going to move on. We shall look at the problem, the dynamics of a rolling coin using the Lagrange formulation. Okay, so rolling coin using the Lagrangian formulation. What we will see here is we have to assume a couple of things. We're going to assume one thing. We're going to say that the coin is rolling without slip. Okay, so we're going to assume that the coin is rolling without slip. Okay, and what we will see is that the coin, if it is rolling without slip, is going to end up being a non-holonomic constraint for the problem. Okay, this will end up being, okay, the idea of rolling without slip in 3D. So this is a 3D problem. Okay, 3D problem. This will end up being a non-holonomic constraint. Okay, and we will see this, of course, in the process of solving the problem. And for this particular problem, as I mentioned at the beginning of this lecture, we will be using the idea of Euler angles. Okay, we will use the idea of Euler angles, and the sequence that is used for this particular problem is called as the 3-1-3 sequence. Okay, I will not be going into the details of the dynamics of how the Euler angles originate. We have to go a little bit into the matrix theory for these things. I will be, of course, posting these on Carmen, so the derivations will be posted on Carmen. I just want to make a note of that as well for this one, just for the Euler angles. Okay, derivations will be posted on Carmen. Post the derivation one carbon. Okay, what we will be doing is we will make use of the essence of this idea in order to understand our particular problem. Okay, so first thing is we need to start looking at the basic problem and see, okay, what are the configuration coordinates. Then we start looking at, okay, what is the constraint on this problem. So how many configuration coordinates, how many constraints, and then once we have an idea of what these are, then we can say that, okay, I'm going to have either a holonomic or a non-holonomic system. If I have a holonomic system, then I will have generalized coordinates, but if that is not the case, as is the situation in this problem, unfortunately, we will have a non-holonomic set of constraints, and we have to, if you want the forces of constraint, you have to use the Lagrange multipliers, but if you don't want them, then we perhaps don't need to. Okay, we will see there are ways of circumventing through these things here. Okay, first thing is we got to set up the problem. Okay, setup of the problem of a rolling coin. Okay, so let me start off by drawing an XYZ coordinate frame. Okay, so this is X, Y, and Z. So the Z axis is vertical for me here. Okay, and here is my Y direction, and the X direction right here. Okay, and let me try drawing a coin that is tilted. Okay. And it's I guess that doesn't look like a circular body. All right, so that looks pretty decent to me. Okay, what I want to do is so I want to look at the situation here, and we want to label some terms. Okay, I guess I want to bring it to the right orientation. All right, so I have the situation here, so I'm going to call the center of mass of the coin as G. Okay, so this is going to be point G. I'm going to say that there is a contact point which we will call as the point C. Okay, and so what are the things that are necessary in order to decide what the configuration coordinates for this coin are? First of all, I'm going to label my axes. So this is going to be the EX coordinate frame. Okay, this is going to be EY, and then this is going to be EZ. And as I said, we will just get started into the dynamics of the rolling coin in this lecture, and then the next lecture we will go pretty much deep into the dynamics of the rolling coin and deeper into the Euler angles and so on. Okay, so here is what I want to draw first. Okay, so starting from here, I want to draw a line that passes through the point G and the point C, and you can immediately see that if I draw another line here which is parallel to the Z direction, so if I just draw a straight line, okay, then there is an angle between these two. Okay, so here is the angle. I'm going to call that angle as an angle theta. Okay, so that's going to be called theta. Let me take this guy and slide that a little, reduce the length of this axis. Okay, just so I have more space to write things. All right, so here is the EY direction. I'm sorry, EY. I see some strange stuff happening. Okay, this is the angle theta, and we will have a name for these angles. This is the same as the Z direction here, so this is the same as EZ. Okay, then I have another angle which I'm going to call as the spin angle. I'll label these things. Okay, this angle I'm going to call as the angle psi. Okay, let me still mark that in the black color. So this is the angle psi, and then lastly I'm going to have one more angle. Okay, let's say that at that point in time that is the tangential direction, okay, to the contact surface, and here are two other directions parallel to the x-axis is what I have here, and then that's the y direction right there. Okay, so that's going to be EY, and that's EX, and this angle here I'm going to call it as the angle. I guess I can use a different color for that. That angle is called as angle phi. Okay, and let me say that the radius of the coin is capital R. Okay, so starting from here all the way to there is the radius R, as is the distance from here to there as well. That's the radius capital R. Okay, and let me call this as the point O, and this is a fixed frame. All right, now what are my configuration coordinates for this particular problem? Okay, my configuration coordinates, how do I come up with that schematic? I need so let me call this as point G. This is the point C. Okay, so I need three coordinates to specify the location of the center of mass G of the coin. Okay, then these locations, these we are going to call as X, Y, and Z. Okay, so location of the center of mass is going to be labeled as center of mass G is X, Y, and Z. Okay, then what else do we need? We need three angular variables to describe where the coin is apart from the location of the center of mass. To describe the location of the coin at any instant in time. And the angular quantities that I'm going to be using are the following. Okay, are going to be the angles phi. Okay, phi is a function of time, then theta is a function of time, and then psi as a function of time. Typically these angles have the following name. Phi is called as the precession angle. Okay, the angle theta is called as a nutation angle. Or the lean angle. And the angle psi is called as the spin angle, which is quite evident from the figure. If you look at this figure here, so phi represents the direction that the contact point, the tangent passing at the contact point, will be taking with respect to the x direction, so that represents a precession. Then I have theta, which is if you look at theta, it tells me whether the coin is leaning, which bobbing up and down or so on. So if theta is equal to 0, then it's an upright coin, right? And then I have the variable psi, which represents the spin of the coin. Okay, so those are the variables that I typically use for this particular problem, which means that we have a total of 6 configuration coordinates. Okay, so we have a total of 6 configuration coordinates, and the configuration coordinates are x of t, y of t, z of t, and phi of t, theta of t, and psi of t. Okay, so we have that. The constraint equation is that the coin rolls without slip. Okay, and we will see that this will end up giving us three equations. Okay, this will end up giving three equations, which implies that the total number of degrees of freedom for the system is 6 minus 3, which is equal to 3. But unfortunately we will see that the constraints that come out of this rolling without slip are non-holonomic except for one of them. Okay, which means that the system is non-holonomic, which means that we cannot come up with generalized coordinates in order to look at the equation of motion directly. So we have to make use of the configuration coordinates, and somehow we can make use of these configuration coordinates, but then categorize the writing of the Lagrangian in terms of the angles theta, phi and psi by making use of certain subtleties and relationships, and then we may actually not even need to use the multipliers in this particular problem. Okay, now how do we look at the dynamics of a coin? The dynamics of typically the dynamics of rigid bodies in 3 dimensions is best represented by making use of the Euler angles. Okay, so that's a statement that I want to make. Okay, so the dynamics of rigid bodies in 3D that describe rotational motion and translational motion are best described by making use of Euler angles, and sometimes these are also called as the Tate-Bryan angles. Okay, the spelling for Bryan sometimes is also written as B-R-I-A-N. This is the spelling that I typically know. Okay, by making use of Euler angles, and here is the basic idea. Okay, in the Euler angles we consider 3 rotations of the rigid body from a reference configuration, and by giving it incremental rotational rates about certain axes. Okay, and this enables us to best represent the motion of that body. Okay, so we perform a sequence of 3 continuous rotations of the body about certain selected axes by providing incremental rates of rotation about such axes. Sorry, about such axes. Okay, and these rotational sequences can be of different types. The most common one is the 3-1-3 sequence. Okay, so the most common one is the 3-1-3 sequence, and we have other sequences as well. Sometimes we also have the 3-2-1 sequence. So other common sequence is the 3-2-1 sequence, typically used in aerospace problems, aerospace type problems. Okay, that's something that we will not be doing. And here is the 3-2-1 sequence of rotation that we're going to be doing for our rolling coin. And for the sake of convenience, just because I can't keep drawing a rolling coin really well, as you have seen, okay, I'm going to make use of certain figures that have their precedence from a textbook by this person called Haim Baru. Okay, so some of the figures I just want to make a note. Okay, note for copyright issues. Okay, some of the figures to be shown are taken from a book called Analytical Dynamics by Haim Baru. It's actually a pretty nice book. If you have a chance to get this book, that's actually worthwhile purchase. What they've done is they've tried to solve this problem of the rolling coin using both the Newtonian and the Lagrangian formulation, and I think it's an excellent resource if you really want to have such a type of a book. Okay. All right, so here is a sequence of rotation. So first thing is we consider the coin in its reference configuration. Okay, so the first thing, so how the sequence is performed. Okay, okay, the first thing is we first look at the coin in its reference configuration. Okay, let me write that word carefully. Reference configuration. And this reference configuration is the situation where the coin is lying flat on the xy plane. Okay, so we say that the coin lies flat on the xy plane. Okay, in its reference configuration. Okay, so here is the reference configuration, and let me pull up the figure. I have a nice figure taken from that book, of course. So here is the reference configuration of the coin. I guess I have to reduce the size of this so as to make it fit the situation here. Okay, so this is the reference configuration. Let me label that. Okay, so reference configuration. And in the reference configuration, I'm going to label the axes. So in this situation, I have my three axes as the following. Okay, so this is going to be the EX direction, this is the EY direction, and this is the EZ direction. Okay, and what you can see is that in the reference configuration, if this is the XY plane, you see that the coin has an infinite number of contact points on the XY plane. Okay, this is something that you want to notice. Okay, note in the reference configuration, in its reference configuration, the coin has an infinite number of contact points. This is called a physical singularity. Okay, that's an important statement. So this is a physical singularity because there are an infinite number of contact points, but then what the saving grace for us is that we actually want to have the coin to roll, so we will have at any given instant in time only one single contact point, and of course we are also going to be ignoring the thickness of the coin. The other note that I want to make here is that note we consider the coin to be very thin. So we treat this as a thin circular lamina. Okay, that's maybe let me make that statement here as well. Okay, we consider the coin as a thin circular lamina. Okay, the coin as a thin circular disc. And so typically if you see textbooks in dynamics, they would be talking about the equations of motion for a thin circular disc, but I just think of it as a coin because it's much easier to visualize money. All right, so here is the situation. So here is the reference configuration. This reference configuration is also, the coin is called as a sleeping coin in this position. Okay, the coin is called, let me write that properly, the coin is called as a sleeping coin in its reference configuration. And the basic idea is it's sleeping because the entire coin is lying flat on the XY plane. Okay, that's because of that particular thing on the XY plane, and that's why it's called as a sleeping coin. Okay, now I'll just describe the sequences of rotation, and we will go to the next lecture later on and then look at what is the information that I can glean from these sequences. Okay, so the first thing is we look at the coin in its reference configuration, and then from the reference configuration I give the coin a small rotation about the Z axis. Okay, the other note that I want to make is the following, important. Okay, usually the x-axis is called the 1 axis, the y-axis is called a 2 axis, and then the z-axis is called the 3 axis. Okay, this is just nomenclature. Okay, so common nomenclature. All right, and so the second point that I want to make now, the second point, from its reference configuration, the coin is given an incremental rotation rate, or a coin is given a rotation about the EZ or the 3 axis, EZ axis, by an amount phi dot. Okay, this is an incremental rotation. Notice that this is an incremental rotation rate. Okay, and so here is the situation. So it's given an amount, phi dot is the rotation given about the z-axis. So this is called as the first sequence of the Euler rotation. Okay, this is the first sequence of the Euler rotation, and it's about the EZ or the 3 axis. Okay, and if that is the case, then what happens here is what happens. Okay, I'm going to bring in my figure once again. Okay, so bring that creature here. Now from our previous labels, this was EZ, this was EY, EX, and this was EY. And now what I'm saying is that this coin is given a rotation about the Z axis, and the rate is phi dot. Let me write that in the black color. Okay, this is the rate phi dot, which means that if you look at EX and EY, they form a co-rotational basis of unit vectors. I'm going to label what that means. Okay, so this is called as a co-rotational basis. Okay, which means that this is essentially a basis, set of basis vectors, unit vectors that rotate with the body. Okay, so this implies that EX, EY, EZ are a set of rotational, set of unit vectors that rotate with the coin or body, or they're also called as a body fixed rotational basis. Okay, they're also called body fixed frame. And of course, outside this body is the fixed frame, and you can think of the fixed frame as some E capital X, E capital Y, E capital Z. At that point in time, it can be coincident with EX, EY, and EZ as shown here. Okay, so this is not necessarily a fixed frame that I have here. Okay, this is a co-rotational frame. So after the rotation has been done, here is what the situation is. Okay, you will see that this axis, after the rotation has been done, this is rotated by an amount phi. Okay, this is also rotated by an amount phi. Okay, which means that now the EX and EY directions are going to be rotated, and so I'm going to have new directions. So I'm going to call them as E1 prime. Okay, and this I'm going to call as E2 prime, and then E3 prime is the same as EZ. Okay, so just to make a note. Okay, so note here, I think I usually use the black color, red color for the note. So note EX, EY, and EZ here form a body fixed or co-rotational basis in the first sequence of rotations. The axes EX and EY and EZ are rotated along with the coin by phi dot about EZ, so that EX and EY are rotated by an angle phi and take a new position. Take a new position, E1 prime, E2 prime, E3 prime of course is the same as EZ, because the rotation is performed about EZ. Okay, all right, and so this is the first sequence. This is the first three sequence, and I can write that here on the problem itself. Okay, on the figure itself. So this is the first sequence. Rotate about 3 axis. Okay, the 3 axis is the same as the Z axis as we have specified. Okay, then we come to the second rotation. Okay, then this is point number 3. Okay, we perform the second sequence, second rotation in the sequence. We perform the second sequence in the we perform the second rotation in the sequence. I'm sorry, I get my English mixed up. Somehow today is not my day. We perform the second rotation of the sequence. By rotating the coin about the new E1 prime axis by a rate theta dot, such that the unit vectors E2 prime and E3 prime, okay, these unit vectors E2 prime and E3 prime will be rotated by an amount theta with the rotation performed about the new E1 prime axis, okay, with the rotation taking place about the new E1 prime axis. And so this is called as a one axis rotation. And so just to reiterate, okay, we perform the second rotation of the sequence by rotating the coin about the new E1 prime axis by a rate theta dot, such that the unit vectors E2 prime and E3 prime will be rotated by an amount theta with respect to their original positions, with the rotation taking place about the new E1 prime axis. This is a one axis rotation. First was a three axis rotation, now is a one axis rotation about the new one axis, okay, about the new one axis, which is E1 prime. And what I'm going to do is I'm going to bring in my previous figure. Okay, this was the first sequence, as I mentioned here. Let me write this a little better. Okay, three axis, about the three axis. Okay, that's an S there. Okay, I'm going to take this figure and I'm going to copy that because I need it. Then I can come back here and paste it. I guess I got to paste the image. Okay, so that's one thing that we had already done. I can perhaps get rid of this creature here, maybe not. I guess not. Okay, which we don't need really. Okay, now I perform the second sequence of rotation. So this is the first sequence, and then for the second sequence I bring in another figure. Okay, this is the second sequence that I perform. Okay, let's say I put it here. Now, important thing. Okay, what did we have before? What do we have now? Okay, previously this was easy. All right, this was E3 prime. Okay, and then likewise this was I guess I had different colors for that, and so let me do the same thing here. This was E, you got to be careful, and this was E3 prime, and this was E2 prime. Okay, and this guy here was E1 prime, and the rotation is performed about this axis by an amount theta dot, and I'll show you a better view of this, such that these guys will travel by an angle theta, and of course this is going to travel by an angle theta, and so I'm going to have a new set of axes now. Okay, this is going to be called as E2 double prime, E3 double prime, and E1 double prime, which is the same as E1 prime. Okay, so this is the second sequence of rotations. Okay, this is the let me expand the figure a little more so that I can add the caption here. Okay, I guess I don't need that. Let me write the second sequence here. So this is the second sequence, and this is rotation about E1 prime, or the one axis, so that I get the new system. Okay, so let me join these here. Okay, so I go from here to there, which means that I have a new set of axes. So after the second sequence of rotations, I have a new set of axes. After the second rotation in the sequence, the axis is now labeled as E1 double prime, which is equal to E1 prime because I'm rotating about that axis. Then E2 double prime, that is a double prime there, and then an E3 double prime. Okay, and this is the contact point, and I guess there is a better picture I can show you here. And the rotation, and I'll show that in the bottom page. Okay, the rotation is performed. Rotation rate of theta dot. This is an infinitesimal or an incremental rotational rate. Incremental rotational rate. Okay, this is the second sequence of rotations, and then the third sequence of rotations is going to be the following, and this is the last point, and we'll conclude our lectures after this. We'll come back to all these again. Okay, the third rotation in the sequence is done by saying that the basis E1 double prime, E2 double prime, E3 double prime is not a co-rotational basis, is not a co-rotational basis. And what we are essentially saying is that since it's not a co-rotational basis, I am rotating with respect to this E1 double prime, E2 double prime coordinate system, or unit vector system, by an angle psi, which is going to capture the spin of the coin. Okay, and in this third rotation, so we perform a rotation of rotation about let's say a rotation about the E3 double prime, or the new 3 axis, by an amount psi dot, which represents the spin of the coin. Okay, this implies that essentially we're now going to have a new set of coordinates. Okay, a new basis. We'll have a new basis, which I'm going to call as E1, E2, E3, which is going to be drawn as shown. Okay, so I'm going to bring in a figure. That's the figure. Once again, I guess this is not the figure that I want. Okay, apologies. The figure that I want is right here. So I bring this creature here. Okay, this is what I had before, after the second sequence is performed. So I'm just going to label only that. So here is going to be one of them. So this is going to be E1 double prime, E2 double prime, and then this is E3 double prime. And the important thing is this: I'm going to now rotate about this direction. The rotation rate is going to be psi dot, so that I'm going to have a new set of coordinate frames, which is starting from here. Okay, we're going to label them here. Then I'm going to have one more there. Okay, and I'm going to call these as E1. This is going to be E2. And look at this angle, which is going to be labeled here, is going to be the angle psi. Okay, and so this essentially implies that E3 double prime is the same as E3. And so this is the third rotation in the sequence. Okay, so the first one was here, this is the second in the sequence, this is the third sequence. Okay, and this is a rotation about the E3 double prime axis, or the new 3 axis. All right, and as we said, the E1 double prime, E2 double prime, E3 double prime, we say this is not a co-rotational basis. This is just so that the contact point can be still given by means of using the E1 double prime, E2 double prime, E3 double prime coordinate frame. So it essentially means that this coordinate frame is not rotating with the coin. I'm just taking another coordinate frame and setting it up such that I get this angle phi that captures the rotation of the coin, or the spin of the coin. Okay, so here are the 3 sequences. I have the first sequence of rotation about the 3 axis. So this is the 3 sequence. Okay, this is the 3 sequence. Then I have the 1 sequence, which is here, and lastly I have the 3 sequence once again, which is why this entire set is called as the 3-1-3 sequence, or the 3-1-3 Euler rotation. Okay, all right, so we will take up all of these, and then we will see how we can make use of these to understand the dynamics of a rolling coin in the next lecture. Okay, thank you for your patience. I hope all of you are doing well. Take care of yourself. Okay, and I'll talk to you all on Thursday during our online lectures. Okay, thank you. Bye bye.